Inside a Formula One combustion chamber at peak operation, metal doesn't simply get hot, it undergoes intense physical stress. The sheer volume of heat generated by thousands of detonations per minute pushes the strict limits of material tolerance. For the 2026 season, the FIA has drawn a hard line. They have capped the geometric compression ratio at exactly 16.0 to 1. In the past, teams engineered their engine components to pass that 16.0 to 1 measurement while sitting on a bench at ambient, room temperatures. But on the track, thermal expansion takes over. At 130 degrees Celsius, the combustion chamber shrinks, artificially pushing the compression ratio past the 16.0 limit for extra power. To eliminate this, the FIA rewrote Article C5.4.3, banning any mechanisms that increase compression while running. Maximizing thermal efficiency is no longer a localized mechanical puzzle. It is a strict compliance barrier that forces manufacturers to completely re-engineer how they deliver power to the wheels. This combustion constraint collides directly with the second major mandate for 2026, a roughly 50-50 power output split between the internal combustion engine and the electrical energy recovery system. Leaning on electrical energy completely rewrites the V6 engine's duty cycle. It must act as a power generator as much as a propulsion device. Because this exact hybrid architecture has never been raced in Formula One, decades of historical dyno data and legacy engine maps are effectively useless. If engineers miscalculate the combustion engine's thermal efficiency under that strict 130-degree limit, the battery system will be forced to overcompensate to maintain speed, leading to rapid thermal degradation. Under a sprint scenario, rapidly deploying both the combustion and electrical systems creates a heat soak that threatens to overwhelm both power units simultaneously. Facing a total lack of legacy data and uncompromising thermal limits, teams must solve the entire powertrain computationally long before a single piece of metal is cut. To map out this uncharted territory, the engine must first exist entirely in software as a complete digital twin. For Ford and Red Bull powertrains, the backbone of this simulation relies on their enterprise software partnership with Siemens. Hundreds of staff across the newly formed Red Bull Powertrains division use Siemens NX to run concurrent CAD engineering, iterating on hundreds of design evolutions simultaneously. They deploy SimCenter Star CCM Plus to run complex computational fluid dynamics, calculating exactly how fuel and air mix inside that tightly constrained 130-degree cylinder. But calculating combustion is only half the equation. That aerodynamic fluid data must be perfectly synchronized with the hybrid battery management strategy. To bridge this gap, Ford Racing runs XROM, a proprietary simulation environment capable of operating at roughly 1,000 times real-time. Looking at this telemetry trace, we can see exactly how calibration engineers use XROM to shape control logic. The simulation defines the precise millisecond to deploy electrical energy versus raw engine power. In a high-load sector, the system instantly spikes combustion to protect the battery, sacrificing a fraction of lap time to preserve thermal health. In modern F1, control software and energy strategy dictate performance as heavily as the physical piston design. The engineering bottleneck has shifted from raw mechanical theory to the speed of computational iteration. In the context of the 2026 rule reset, traditional motorsport manufacturing has a fatal flaw: physical time. Historically, producing a single complex combustion component through standard casting and milling could take up to 16 days. To bypass this delay, Ford utilizes industrial 3D printing, specifically laser powder bed fusion, to construct parts layer by layer. This process compresses the production cycle for prototype components from 16 days down to just 5. Engineers are already fabricating intricate charge air hardware and complex energy recovery components using this additive process. These freshly printed parts are immediately shipped between Ford's facilities in Michigan and the Red Bull factory in Milton Keynes for continuous dyno testing. Established manufacturers arrive at 2026 with over a decade of legacy hybrid experience. Buying back development time through rapid physical prototyping is the only way a new entrant can catch up. Cautionary: additive manufacturing introduces a severe risk is not tightly controlled. Standard 3D printed metals lack the yield strength required to survive the extreme forces of an F1 combustion cycle. Red Bull Powertrains counters this through rigorous technical control, tracking the exact provenance and chemical composition of every batch of raw metal powder before it enters the printer. During the print, parameters like laser hatching and layer thickness are minutely tuned to ensure the mechanical properties of the alloy aren't compromised during fusion. But the critical step happens after the part is built, the heat treatment phase. Laser printing builds up immense residual stress, trapped as a warped, compressed crystalline lattice. Through microstructure development, precise heat gradients are applied. Alloys are manipulated at the atomic level, relaxing the residual stress to maximize fatigue resistance. Mastering this micro-level material science is the only way Red Bull powertrains can physically construct the aggressive geometric tolerances dictated by their digital twin simulations. Digital simulation, rapid additive manufacturing, and atomic-level metallurgy all converge the moment the physical engine is bolted to the test dyno. It operates as a continuous closed loop. The physical dyno data generated in Milton Keynes is instantly fed back into Ford's material characterization models in Michigan, refining the parameters for the very next print. This partnership flows both ways. When the FIA introduced strict new oil separation and consumption limits, Ford leveraged its decades of production car emissions data to solve the problem for the F1 team. Ford views this powertrain as a high-speed R&D lab for its consumer fleet. The thermal and battery degradation strategies developed for 2026 translate directly into the software managing its next generation of road-going electric and hybrid vehicles. F1 provides a high-stress environment to develop real-world solutions for charge optimization, precision thermal control systems, and structural fatigue management in performance road cars. The 130-degree compression limit transformed F1 engineering from a mechanical puzzle into a data-driven science. By forcing the integration of atomic-level material science and hyper-fast simulation, these regulations accelerated the technology defining the next generation of high-performance hybrids.